Okay, so everyone's being recorded. So welcome back to the RL Theory seminars again for this week. So, so the way this works is the presentation will be 50 minutes, around 50 minutes. So it should be done around 5:55 UTC. And throughout the presentation, feel free to ask like any questions. You can ask in the chat. If you ask in the chat, I'll just say it. Like I'll read it out for you, and I can ask Dylan. And you can just unmute and feel free to ask like that during the presentation as well. Also, there's going to be a Q&A at the end of the presentation. So if you have like a longer question, just maybe wait till the end so we can get through the presentation. And today we're going to have a co-host. So Nan will be the technical co-host who's going to stimulate Dylan with some exciting technical questions and get him, I guess, maybe, yeah. So, and then I guess other than that, I'll just go ahead with introducing Dylan. So Dylan Foster is a senior researcher, and he currently works at Microsoft Research in New England. Previously, he was a postdoc at MIT, and he received his PhD in computer science at Cornell University, advised by Karthik Sridharan. And his research focuses on problems on the intersection of machine learning and decision-making. And recently, he's had an emphasis on reinforcement learning. And he's also received some awards. He's got the Best Paper Award at Calton 2019 and the Student Best Paper Award at Calton 2018 and 2019. And I guess without further ado, Dylan, you can get started.
Cool, thanks a lot. Yeah, if there's any of you hearing me, just let me know. Yeah, so this is going to be a talk about what I'll call like interactive decision making. And yeah, when I say interactive decision making, in this talk at least, what I'm going to be thinking about is problems where we, have an agent interacting with an unknown environment and, sequentially making decisions like, what treatment do we give to a patient? What signal do we send to a robot's actuator? And we're really going to be focusing on problems where we're trying to do this in a data-driven fashion, right? We want to be like learning to model the environment on the fly as we're making decisions so that we can improve the quality. So this is a broad problem. There's many different ways you can model it and try to like tackle it depending on the domain. Contextual bandits is this formulation that's widely used in online recommendation. Reinforcement learning and control are these like more general and powerful formulations that you see applied to tasks like robotics. And there's many other like interesting formulations you see across like, domains like personalized medicine or operations research. And so what we want to explore in this talk is, okay, given that we have all these different domains and different formulations for how to do interactive decision-making, can we get some kind of like unified tools for designing algorithms and to like understanding sample complexity and statistical considerations so that we can kind of focus just on modeling and not, have to work on like algorithm design when we encounter new problems. So the plan for the talk is going to be as follows. We're going to start by formally setting up this interactive decision-making problem and highlighting some challenges. And then I'm going to introduce this tool called the decision estimation coefficient, or the DEC, which is a tool that we introduced in previous work by myself and others that tries to give like a unified approach to solving and understanding decision-making problems. But what I'm going to do is I'm going to highlight some gaps in the best possible results that we were able to like achieve using the DEC. And the main point of this talk is going to be to highlight some recent work we've been doing that kind of closes these gaps to the best extent possible and gives more refined guarantees. And this is really going to be kind of like a narrow technical talk. Like all I'm really hoping to do here is just get across like what are the main new results, like how do we prove these? So with that in mind, yeah, let's get into the setup. This first little segment should be a little familiar if you saw the talk I gave on the original DEC paper last year. I just want to make sure everyone is on the same page though. So for this talk, because we want to be able to look at many different decision-making problems, we're going to adopt a general framework that we call decision-making with structured observations, which is just going to give a convenient way of like describing many different decision-making setups in a unified fashion. So the setup here is we play for capital T rounds, where each round little t, we select a decision pi t. And then based on this decision, we receive a reward RT and some kind of auxiliary observation OT. And our goal here is just to, select these decisions to maximize the total reward over all rounds. So this should be familiar, if you've looked at bandit problems. I'll show in a second that this also encompasses like episodic reinforcement learning problems, but I'm first going to try to get through some more details. So first of all, we're going to be considering a stochastic version of this setting. And what this means is we have what's called a model M star, which is just a conditional distribution that maps the decision we select to, the distribution over rewards and observations. So we're just assuming here that at each time t, when we pick pi t, the reward and observation are drawn from M star. So M star here in this setup, you should think of this as representing like the environment that we're interacting with. Like for RL, this will be an MDP. And this is not known to the learner. So, the only way we get information about M star is just by taking decisions and seeing what happens. We are going to assume, though, that M star belongs to some known class script M. We'll call this our model class. And this kind of like encodes our prior knowledge about the problem in the way that like a hypothesis class would encode our prior knowledge if we were doing like supervised learning. And I'll give examples for this in a second. Before I do that, the last thing to mention here is we're just going to measure performance through regret. And this is just the difference between the cumulative reward for the optimal decision, like if we knew the underlying model, and the cumulative reward for the actual decisions that we select. And just a notation here, okay, FM pi, this is just the expected reward for decision pi if M is the underlying model, and pi star is just the optimal decision for M star. Okay, so that's regret. We will also briefly touch on like simple regret or pack guarantees in this talk, but the main focus is going to be on regret. Okay, but let's make this more concrete by looking at a couple of examples. So the simplest setting we can look at here is the multi-armed bandit. This is just this familiar setting where at each time I pick an action, that's what we usually call decisions in the setup from a finite set, 1 through big A. And then I see a reward based on this, and I don't get any other feedback. So here, there's no observations besides rewards. So O is the empty set. Our decision space is just this finite set 1 through big A. Our model class is just going to be like all possible reward distributions, maybe subject to being like bounded or sub-Gaussian. Okay, multi-armed bandits, that's like an unstructured problem. There's no assumption on like the reward distribution, but we have a small finite decision space. If we change what our model class is, we can capture settings where you have like a lot of decisions, but you have structure in the rewards that allows you to generalize, right? So like linear bandits, this is this example where our decisions live in R to the D, but our reward functions, these are somehow like linear in like the decision or linear in some featureization of the decision. The way you can capture that in this framework is just by restricting script M to only contain reward distributions that are linear, right? Okay, and you can generalize that idea, right? Like so non-parametric bandits, similar, but now we're only assuming the reward functions are Lipschitz. Again, the way you incorporate this is just to say, script M consists of like all models with Lipschitz reward functions. Okay, naturally, there's many other types of structure you can explore. Okay, but moving on, I haven't talked about the observations at all. The last example we'll look at here, which is a setting where the observations are important, is RL. And we're just going to look at an episodic finite horizon reinforcement learning setting. So here, our model will be an episodic MDP with horizon H. So this means we have a state space S, an action space A, transition distribution P, reward distribution R, and an initial state distribution. And what happens for each episode in this MDP is, we sample the initial state from the initial state distribution D1. Then for each step, little h equals 1 through big H, we pick an action by applying some policy to the current state. Then based on the state and action, we see a reward drawn from the reward distribution. We see a next state drawn from the transition distribution. Okay, and that's just one episode. When we apply this in the general framework we've been looking at, we have an underlying MDP. And what happens is that each episode, we pick a policy and execute it. we see a trajectory generated through this process, and that's going to give us our observation. Like the observation here is just a sequence of states and actions and rewards. And yeah, our goal is to maximize the cumulative reward across all episodes. So that's the basic RL setup. The one thing I want to emphasize here is like your model class and your model, this is parameterizing what the transition probabilities and the rewards look like. So your model class is capturing prior knowledge about the MDP, and as this kind of list is showing, there's many different ways that you can do this. You've got your classical examples like LQR. You have many much more like rich and sophisticated structures that have been explored over the last few years. Okay, and so to summarize and kind of like wrap up this setup, the point of this general decision-making kind of framework here is just to have a simple way of viewing what you can see is like a pretty broad class of decision-making problems through the choice of your model class script M. So in general, like what kind of modeling assumptions work well? This is going to be somewhat domain specific. And we would like to not have to start from scratch every time we encounter a new domain. And so this is going to lead us to ask, can we have something like a unified notion of problem complexity that can meaningfully capture the optimal statistical complexity for any model class script M? And when I say like statistical complexity here, all I'm really asking is like, how is the optimal regret or like the minimax regret? How is this determined by the horizon T and the model class script M that you're working with? The hope here is kind of that like if we had a notion of problem complexity like this, this could perhaps guide us in designing, new algorithms when we encounter new domains, and maybe would lead us to general purpose principles. Okay, so to briefly motivate the new results I'm going to present, I just want to give a quick kind of sense for like why is it challenging to get a handle on the statistical complexity in these general decision-making settings. And the point is that this is really a combination of both statistical challenges and algorithm design challenges. Like these cannot really be decoupled. And we're just going to do this by walking through a couple examples of different model classes and seeing what makes them easy versus hard. Okay, so what I'm showing on this slide, this is going to be like a bandit problem or a bandit-like problem where our goal is to, maximize some underlying reward function. And the only observation or feedback we get when we make a decision is the reward itself. So for this example, our model class has these three models in it, M1, M2, and M3. And this graph here in the middle of the screen is just plotting the mean reward function for each model in the class. So this example is kind of what I'll call an easy or like a trivial problem. Like we have multiple different models, but you can see from the graph, they actually all agree on what the optimal decision is. And so that means like if I know in advance that the optimal model is in this class, then like a minimax optimal algorithm is just to commit to playing this one decision that they all have as the optimum in advance for every round. Like I don't need to explore or even bother figuring out what the underlying model is to do well. Okay, now I've changed the model class slightly. So now if you look, you'll see the different models have distinct optima. So this is more like closer to a typical bandit-like problem. And here, in order to optimize the reward, we will actually need to explore the decision space. Like we're going to need to test like, okay, is the peak over on the left? Is it over on the right? And so on. And like in general, without further structure, the best regret we would hope to achieve here will scale with like the number of possible optima. Okay. And now I'll change the model one last time. And here, what you'll see is like we still have different optima for different models. But now over on the right, we have like a single distinct decision on the x-axis, which is not optimal, but it's a decision where the reward functions all take on like very different values for the different models. And so for this model class, yeah, if we know the underlying model is in this class in advance, an optimal strategy is just to query this point over on the right a bunch of times and estimate the function value at this point. And once we do this, we can just kind of like infer the underlying reward function and hop to the optimum. So what we ended up with is just, a setting where by changing the function value slightly again, we now again have an easy problem where we don't really need to do exploration. Okay, so I hope these examples kind of convince you just that there's a lot of subtle factors and like different features of problem instances that can affect, the optimal regret for decision making. And sometimes this happens in kind of like surprising ways. And as you can imagine, these only kind of get amplified when you move beyond like simple bandit problems like I was showing to these more rich problems like RL, where now the decisions and the observations are very like high dimensional and structured. And I think, in light of all these different factors, it is natural to ask, like, should we even hope to have like a single notion of problem complexity that can, meaningfully capture the optimal regret for any decision-making problem? But what it turns out is like, okay, I would say you can do better than you might think. So we had this recent work with Shyam Kakade, Jen Khan, and Sasha Rocklin, where we gave this complexity measure called the decision estimation coefficient, or like the DEC. So the DEC is necessary to achieve low regret. And okay, with a bunch of caveats that I'll mention, it's also sufficient. But unfortunately, like our results in this work, they left some gaps between like the best possible and upper and lower bounds on regret that the DEC gives you. And this kind of prevented us from giving like a complete characterization of, what is really the best possible regret that you can get as a function of your model class. And so what I'm going to do right now is, give a quick recap of like, what is this decision estimation coefficient, or the DEC? And then the main point of the talk will be to, present this recent work that tries to kind of like close these gaps to the best extent possible. Questions before I move on to this part? Okay. So, I'll dive right into this DEC. So I'm displaying the decision estimation coefficient here. For reasons that will be apparent once I kind of get to the new results, we'll call this like the offset version of the DEC, or like the offset DEC. And this is going to have like 3 different parameters. So one, of course, is going to be like our model class script M. The next parameter will be what we call a reference model M bar. And then the last parameter will be this scale parameter, gamma. Okay. So I'm displaying this full expression here. This is, okay, there's a lot going on, but I'll walk through this step by step and like give the interpretation. So the DEC, the first thing you can see here is it's a min-max game. I'm highlighting the min players variables in red and the max players variables in green. And it's a game where the min player, which kind of represents the learner, they're trying to find a distribution P over decisions such that if we take a worst case model in the class chosen by the max player, this is kind of representing nature, we want the suboptimality of the decision sampled from P, like the instantaneous regret under M. We want this to be balanced by a notion of like information gain relative to this reference model M bar. So here we're kind of quantifying information gain using Hellinger distance. This is this information theoretic divergence. And what we're looking at is like, what is the distance between the distribution over rewards and observations induced by the decision that P selects? So the distance between M and M bar. Okay, and if you want this information gain to be large, you should be picking a decision where the corresponding, distributions for these two models, these are very different. So, okay, at a high level, to summarize this, M bar, you can kind of think of as a guess for the true model here. And this DEC is just asking, like, what is a strategy for the learner that achieves the best trade-off between the instantaneous regret and the information we acquire in the face of an unknown environment? And the scale parameter gamma is just controlling this trade-off, like how much regret are you willing to pay to gather information? Okay. Yeah, and just one remark here. Yeah, you can imagine using KL instead of Hellinger distance if this is more familiar to you. This is not super crucial for any of the results.
But KL you can run into unboundedness, right?
Yeah, I mean that's why we're using Hellinger. Okay. But like you can smooth things out. Like if you make like if you make those mild assumptions on your problem, you can like smooth things
out.
Right.
The other quick thing is that so later, if I remember correctly, again take another max over m bar. Is that correct?
Yeah.
Because you don't know what the true model is.
Yeah.
You have to do worst case reasoning.
Yeah, so I'll get to that like literally right now.
But related, so here the inside max over m, the green m,
Yeah.
that's also worst case reasoning, right? So you're in
Yeah.
wait, or is it best case? Like which direction?
No, the max over m is like worst case. Like this is really
Worst.
just like a proxy for the fact that you don't know m star.
Okay, sure.
Yeah.
Okay.
Cool. Yeah, so I'll get right into that. So let's look at the upper bounds and the lower bounds we get based on this offset DEC. So on the upper bounds, what we showed in this work is, yeah, if you run this algorithm that we call estimation to decisions, you get a regret bound that's controlled by the DEC, plus a term I'm going to call ST in this talk, which kind of represents the complexity of performing supervised estimation with the class script M. So your regret has two terms. One is this DEC at scale gamma times T. The other is gamma times this quantity ST, which, yeah, like I said, this is kind of like you should think of this as just like, what is the minimax rate for doing like conditional density estimation with the class script M? So this is always going to be bounded by the log cardinality of the class script M, and I will often use these interchangeably in this talk. But informally, what this result is saying is, if the DEC is small and you can perform estimation well, you can have low regret. The DEC is going to be decreasing in gamma. So you can see that like you're going to want to pick gamma to balance this first term and this second term. Okay. Now on the lower bound side, you have a minimax. You have a lower bound on the minimax regret in terms of the DEC. This is going to say like for any model class script M, the regret of any algorithm has to scale again with two terms. One is the DEC at scale gamma, but now it's going to be for a subset of the original model class script M, which we call a localized model class. And the other term is gamma itself. So this is like the same term in the upper bound, but without this like estimation term. Yeah, and so to interpret these, like you can see that these have similar expressions, but these are not exactly the same, right? And I'll walk through these differences and kind of explain the interpretation. So the upper bound here, the first, and yeah, I'll just kind of explain like what are the gaps between these bounds. The first gap here I'll show is, yeah, the upper bound, we're evaluating the DEC on this full class script M, while the lower bound, we're evaluating it on this subclass M prime, which roughly, right, is just constraining to models where the mean reward function is like uniformly close to the mean reward function M bar. That's why we say this is localized. It's like a neighborhood around M bar. Next gap, which this is related to the question that Nan was just asking, is the upper bound is taking the max over this reference model M bar in the convex hull of the class script M, whereas the lower bound is taking the max over M bar just in the original class, which is a smaller set. And informally, this is happening because for the upper bound, M bar kind of represents like an estimator that you get out of an online learning algorithm, which in general is going to be like an improper mixture. Okay, and the last gap here is just the upper bound has the second term where gamma multiplies the estimation complexity, whereas the lower bound just has gamma. It's not multiplying anything. Okay, so those are the main gaps I wanted to mention. Like in spite of these gaps, you know, these are still sufficient to derive like interesting and like in some cases tight regret bounds for many classes of interest, at least up to like, you know, kind of like polyfactors. But these do fall short of giving a total characterization for when low regret is possible. And that's going to lead us to like the new results I'm going to present.
Yeah, but before we move on, like, I don't understand how, relatively speaking, how severe each one of these is compared to the other, right?
Yeah, so I'm going to come back to that. I'm going to come back to that.
Okay, so maybe a quick thing is like the convex hull thing doesn't seem a big deal because I think in some of the standard models we're interested in, like it seems like they're convex already. Right?
Some are not, okay. Right? So like MDPs are not convex. Like a mixture of two MDPs is not convex.
Okay.
But like, okay, just to give a spoiler, we're going to resolve this issue. So the answer here is like the M bar in the lower bound actually should be in the convex hull as well. Yeah. Cool. Okay, so yeah, in what follows, what I'm going to try to do is I'm going to introduce a new version of the DEC, which we call the constrained DEC. And I'm going to show that it allows us to kind of remove these gaps to the best extent that you can hope for. Yeah, and kind of like achieve, I think, like, the best guarantees that one can imagine getting without just moving on to a totally new complexity measure. So I'll also just show that this constrained DEC, in addition to giving guarantees for regret, will also give guarantees for PAC. And yeah, I'll also just try to spend a little bit of time going through what are the key proof ideas here. And I should mention at this point that this is based on joint work with my excellent collaborators, Noah Gulwich and Yeonjun Han. Okay, so this is going to get us into the sort of main content of the talk. So what I'm displaying here is a new variant of the DEC that we call the constrained DEC. And you can see that I've put a C superscript on it to distinguish it from this previous version of the DEC I was showing, which, yeah, we usually call the offset DEC. Okay, so this constrained DEC, there's really only one change here relative to the offset DEC, and that's just how do we handle this Hellinger term, this information gain. So you'll see, instead of having this scale parameter gamma, we have a new parameter that we call epsilon. And, instead of subtracting off the Hellinger distance between the models M and M bar, we're now putting like a hard constraint on the Hellinger distance. So in particular, we're asking that when we take the max over M in the definition, we want M to have Hellinger distance at most epsilon squared relative to M bar under this distribution P chosen by the min player. Okay, so that's it. Like, that's the whole difference. And yeah, all that's really happening here is, instead of implicitly encouraging the max player to have low information gain, which is what happens in the offset DEC, we're now just putting a hard constraint on the information gain. So you might see these definitions like this offset DEC and this constrained DEC. And like probably the first thought you have, right, is, okay, this offset DEC, like obviously this is just a Lagrangian relaxation of the constrained DEC, right? So, I mean, that's true. And you might imagine that, these should be equivalent by duality. But what it turns out is like strong duality does not hold here. Really because the optimization problem we're looking at is not convex with respect to the max player, the M player. So these are not equivalent in general. Now the constrained DEC, this is never larger than the offset DEC. That's what this displayed equation is showing. But in general, it can be much smaller. And so this simple difference, like this kind of seemingly small difference of putting a hard constraint on the information gain, this can actually meaningfully change the behavior of this complexity measure. And this is going to be key for deriving, tighter results, which I'll present now. So let me give a quick overview of our main upper and lower bounds that we get based on the constrained DEC. So to present these, I'm going to define this quantity in the green box here, which is what we get by starting with the constrained DEC and taking the max over this reference model M bar in the convex hull. One thing you'll notice here is I'm also actually taking the union of script M and M bar in the first argument. So this actually turns out to be pretty important for technical reasons that I'm not going to have time to get into in this talk, but you can check out the paper for more details. Okay, but what we can show is, so for any model class script M, the optimal regret for any algorithm is going to be upper and lower bounded by this constrained DEC times T for different choices of this scale parameter epsilon. So for the lower bound in this result, we're setting epsilon to be 1 over root T. And for the upper bound, we're setting epsilon to be the square root of the estimation complexity over T. So like root log M over T. So that's kind of the main result. To interpret this, I want to kind of give an overview of how this stacks up against the previous bounds that I was showing. And this is going to be related to Nan's question. But I will also just go through some quick examples to just give a sense for what is like the scale of all of these different quantities. Okay, but first let's come back to these gaps. So you remember the first gap I mentioned in these guarantees based on the offset DEC, that was this issue of like localization, right? The upper bound had the full class script M, the lower bound had this smaller subclass script M prime. So you can see in our new results, we're just getting rid of this localization thing entirely. Like the lower bound and the upper bound, they just have the same class, okay? Okay, now we'll go to the second gap. So you remember in the old results, the upper bound took the reference model M bar to be in the convex hull, while the lower bound just took it to be in script M. In the new results, both the upper and lower bound take M bar to be in the convex hull. And so this is actually pretty interesting. This is showing that somehow these like improper reference models are actually like fundamental. Okay, and now the third gap, that was this role of the estimation complexity, where the upper bound scaled with the log cardinality of this class script M, the lower bound did not. So the new result still has this gap. And this turns out to be like fundamental. So there are classes for which the upper bound in this expression is tight. There are also classes for which the lower bound in this expression is tight. So yeah, in general, one cannot hope to get better guarantees here without, you know, fundamentally changing the complexity.
Wait, like I guess the nuance here is that the places where the upper bounds are tight and the lower bounds are tight are different.
Yeah, totally.
Otherwise, like, it doesn't make sense. Like, you know, this.
Yeah, totally. No, all I'm saying is like there are model classes where the upper bounds are tight. There are model classes where the lower bounds are tight.
So I see. That's why what you mean. Like, if you still take generally this expression, this is the best you can do because
exactly.
Like, that single expression
exactly
between,
exactly. So like you cannot hope to like, you know, just like improve the epsilon in the upper and lower bound here uniformly, right? So that's what I'm saying is like what remains is just, you know, to go beyond these, you just need to get like a new complexity measure. And that's like statistically, I would say that's like the most interesting open question that we leave. I'll say more about that as we get, well, at various points in the talk, actually. Yeah.
Yeah. So just to clarify, so the issue is like that the DEC can't distinguish between these two types of problem classes, one where the lower bound was tight and the other one where the upper bound was tight.
Yeah. Not at least like in its current form. Like, you know, it's possible that one can come along later and come up with like, you know, maybe some kind of like more refined version of this thing. But like, yeah, in the current form, this is the best that you can do.
And when you talk about like what is actually the structure of these problems and under which these things are like tight and what the DEC misses in happiness.
Slides.
Okay.
Yeah. I just want to give a couple remarks first. Yeah. So the first remark here is like, you know, the improvement you get in this lower bound from removing the localization, allowing for improper reference models. So this can actually be like significantly. So there are classes where the lower bounds can just be arbitrarily large compared to the previous ones. And you can look at the paper for examples of this. On the upper bound side, so the upper bounds we get here can improve upon the previous upper bounds based on the offset DEC, but it's not as significant as the lower bounds. So like the gap between like the old upper bound and the new upper bound, this is never going to be bigger than say like root t versus t to the 2/3. Like these are always within like polyfactors of each other. Okay, the last remark here is like, you know, even though I said this constrained DEC can be smaller than the offset DEC, there's actually a tighter connection between these things, but only if you restrict the offset DEC to a different kind of like subset of models, this which I'm showing here. So roughly speaking, models where the optimal value is not too much larger than the optimal value of M bar. So yeah, you can look at the paper for like the tight connection between these things. This kind of equivalence, this is useful if you want to understand like why are there certain similarities and differences between like the old proofs and the new proofs, but we don't really make use of this perspective to like prove the new results. I would say like working with the constrained DEC directly is really what like enables the new results. And yeah, like for this reason, I kind of think that like, you know, just introducing this complexity measure itself is one of the more important conceptual contributions here. Okay, cool. So let me just go through a couple examples really quick. And this will get at this question of like, when is the upper bound tight? When is the lower bound tight? So if you look at the multi-armed bandit problem with like A arms, so just finite set of arms, but there are A of them. Here, this constrained DEC at scale epsilon grows as roughly epsilon times root A. And you can bound this Hellinger estimation term by A as well. So in this case, what you get is the lower bound evaluates to root AT, which is tight. The upper bound evaluates to root A squared T, which is, off by this extra A factor due to the Hellinger estimation term. You can look at this table for a bunch of other examples. The high-level message here is like you're going to see similar behavior. So for most settings, the lower bound is tight, which is what this last column is indicating. And the upper bound is loose due to this extra log m. But there's some cases where like the extra log m really should be there and the upper bound is tight. So if you look at like linear bandits in D dimensions, here like the lower bound in this theorem is root dt, but the optimal rate is really root d squared t, which is what the upper bound is getting. So that's kind of like a canonical case where the upper bound here is tight, because like somehow for linear bandits, you really should be paying like a factor of d for what's the complexity of exploring the space, which is really what like the DEC reflects. And then you should actually be paying a factor d for like estimating the parameters of this linear model.
So one question about upper bound being tight or not, right? So if I remember correctly, the original DEC paper, the upper bound is realized by you have a particular like information theoretic algorithm that enjoys certain regret and you get an upper bound. So when the upper bound is not tight, there can be two sources. One is that maybe the algorithm is right and the algorithm is actually good, but the analysis of the algorithm gives you the loose bound. Versus maybe that's just not the right algorithm. What case it is?
Oh no, it's definitely just not the right algorithm.
The algorithm is like, the algorithm is
the reason you're paying the log m here, right, is you're trying to estimate the underlying model in like Hellinger distance or like KL, which is like this very stringent notion of estimation. And like for many of these classes, you don't care about estimating distribution. You just care about estimating some sufficient statistics. So like if you want better guarantees, you need an algorithm that is working with a less stringent notion of estimation. And I'll give a specific remark about that and a pointer to a paper that we have that like takes this perspective at the end of the talk. Okay. So those were the main kind of results I wanted to show concerning the constrained DEC. I want to quickly...
One more. Was there an example there where the lower bound was tight and the upper bound wasn't?
Yeah, so all of the green check marks here are cases where the lower bound is tight and the upper bound isn't.
Oh, I see.
In most cases, the lower bound is tight.
I see what you mean.
The linear bandit is where the upper bound is tight. I mean, upper bound is not shown here, right? So this table only shows
I was trying to. I see. Okay.
Cool. So what I want to do next is just give a quick overview of an extension to like PAC guarantees or simple regret. This is just because this is kind of cute to see how like the constrained DEC adapts to this setting. So just to recap here, for PAC guarantees, right? Just like regret, we're going to interact with the underlying model for capital T rounds where, again, at each round, we just select a decision and see the reward and observation. But now for this setting, we don't care about the quality of the decisions we make along the way. Rather, like after the T rounds are complete, we can just pick a final decision pi hat based on all the data we've collected. And we're only evaluated on the quality of this decision, which I'm calling risk here. Okay, so you can adapt the constrained DEC to give kind of guarantees for this setting that are analogous to the ones for regret. And there's just one tiny change you need to make. So, okay, I'm calling this PDEC. The P is for PAC. The only change we're making here is instead of minimizing over a single distribution P in the definition of the DEC, we're going to minimize over two different distributions, P and Q, where the distribution P appears in the regret term in the DEC, and the distribution Q appears in the Hellinger term. Okay, so the interpretation here This is like very simple. Q, you can think of as like a pure exploration distribution that only cares about making the information gain relative to M bar as large as possible. And P is going to be like an exploitation distribution that is just trying to achieve regret that's like as low as possible amongst all the survivors that, or amongst all the models that like survive this constraint under Q. So this is pretty simple, right? Like this is just saying like, because we don't care about like cumulative performance, we can separate out the exploration and exploitation part. Okay, so similar to the regret case, I'm going to define this quantity in the green box, which is just the result of taking the max over M bar. Oh, sorry, this should say PDEC on the right instead of just DEC. Unlike the regret case, it won't be important to take the union with script M and M bar here. Okay, but what we can show with this definition is the optimal risk for any algorithm. This is just, again, upper and lower bounded by the constrained DEC for different choices of this scale parameter epsilon. As in the regret case, you're getting root 1 over root t for the lower bound and getting like root estimation complexity over t or root log mt for the upper bound. And like the regret case, this difference in the scales for the epsilons due to this estimation complexity, yeah, this is really the only gap here. Okay, now that we've kind of seen the main results for the constrained DEC, I just want to spend the last part of the talk giving a little intuition behind the proof techniques and saying a little bit about why having this constraint is helpful. And so I'll start by talking about the proof techniques for the lower bound here, okay? So to motivate the proof techniques, I want to start by highlighting a connection to kind of like classical statistical estimation and like Lecombe theory. So some of you might be familiar with this notion of complexity in statistics called the modulus of continuity, which was introduced by Donahoe and Liu in the late 80s in the context of like non-parametric functional estimation. So this is for the kind of like passive estimation problem where we're getting IID samples from some distribution M. Okay, so here M is just a single distribution. It's no longer a conditional distribution. There's no decisions. And my goal is just to use these observations from the model to estimate some scalar functional FM, right? So FM could be like the mean under the model, or it could be something more interesting. So what you can show, though, is that this modulus of continuity, this is a complexity measure for this functional estimation setting that just says, like, look, if I consider some Hellinger ball around a reference distribution, what's the worst case error in like these functionals? So this leads to lower bounds and under some conditions, upper bounds on the optimal error for functional estimation. And yeah, we think of the DEC as kind of like a decision-making counterpart to this modulus of continuity, like something that extends this concept to interactive and like sequential problems. Like this is a connection we made in the original DEC paper, but I think that the constrained DEC makes this connection like super, super explicit. But the big difference is just like, because we are in an interactive setting, we end up with a min-max problem rather than a maximization problem, which makes this a lot more rich. Okay, now to bring this back home to like, how do we prove lower bounds based on the constrained DEC? I want to recap like how you prove that the modulus of continuity leads to lower bounds for estimation. And this is a very simple technique, which is called like the 2-point method. So the idea here is like, if I set this epsilon to 1 over root t, then the modulus of continuity kind of witnesses that there exists a hard pair of models that, first of all, are hard for any algorithm to distinguish because they have total variation distance. If we look at like the law over data sets they induce, this is at most like a small constant, like a half. Okay, and then the second property here is that if you don't identify the right model from this pair, you have to have low risk. Like this is precisely what the modulus of continuity witnesses. And once you have these two properties, like the fact that sort of any algorithm needs to have risk that scales with the modulus, this is like pretty immediate. So the way we prove lower bounds for the constrained DEC, this has some conceptual similarities. It also has some pretty important differences, okay? So the idea here is we're going to use the constrained DEC to witness a hard pair of models, but kind of because we're in an interactive setting, we're now actually going to choose this pair of models adversarially based on like the specific algorithm you're considering. So the setup here is like, you give me an algorithm, I find you like a pair of models such that the algorithm needs to perform poorly on at least one of them. So in more detail, the way this works is, like, let's say we pick an algorithm A, and then let's pick a reference model M bar. I'm going to use P here to denote like the average play of the algorithm when M bar is the true model. So just like, what is the marginal distribution over decisions across all rounds? And then what we're going to do is set this epsilon to be 1 over root T. And we're going to take M to be the decision that maximizes the DEC when you plug in P for the min player. So if you do this, then what you get is that the constrained DEC, it's going to witness that M and M bar are kind of like a hard pair of models in the sense that they have, yeah, like two properties that make them difficult for the specific algorithm under consideration. So one is they're hard to distinguish in the sense that if you look at like the law of the full like history under M and M bar, this is a constant in TV distance, like a half.
Wait, so where does that constant come from when you set epsilon to be 1 over root T? Like,
oh, good question. This is kind of from like, okay, this is immediate to see if you have KL divergence, but it's like, it's basically like chain rule plus, yeah, it's basically chain rule for KL.
I think of it as something like, you know, that epsilon square that appears in the constraint DEC,
Yeah.
like per round information.
Exactly.
Interact with T rounds, you actually get one more information.
That's exactly right. So it's basically you have
One
like
has to be viewed as like, I mean, I know it's small, like for the purpose of this lower bound.
yeah.
It should be viewed as pretty large because it's a T round total information.
Exactly. So yeah. So basically, like you effectively have 1 over T units of information per round. So when you sum that across all the rounds, you get roughly a constant unit of information.
Okay. Yeah. Okay. And there's also a question in the chat: is reference model class M bar assumed to be constant throughout the interaction process? I guess first of all, it's a single model, right? The M bar is not a model class; it's a single model.
Yeah, M bar is like a single model. So basically, what you do for this lower bound is you pick M bar. You do this whole process for proving the lower bound that I'm describing here. This will give you a lower bound in terms of DEC with M bar. Then you take the max over M bar at the end. But yeah, like okay, if you're asking about interaction, yeah, the models are not changing throughout the interaction. Like we're always.
So I guess you can just view, in this case, M bar as the true model.
Yeah, it's one choice for the true model.
One choice of the underlying true model, which obviously doesn't change over time.
Yeah.
Or it's not even allowed to change over time.
It's not allowed to change. Yeah. Okay. Cool. So yeah, like just to wrap this up. So we have this is kind of, the DEC here is kind of witnessing a hard pair of models where, first of all, they're difficult for the algorithm to distinguish. And second of all, if it fails to distinguish them, its regret is going to roughly scale as like DEC times T, which is what you want. A subtlety though is like compared to the classical 2-point method, we really are picking these models based on the algorithm under consideration. And this is arising because this is an interactive setting. And as a result, like even though it has similarities, you really cannot interpret this as a 2-point method. And like the lower bound here, you know, can indeed reflect hardness that arises from considering more than 2 models. And you see this even for like bandits, right? Bandits, if you have A actions, you're getting a lower bound that scales with A, and you really need to consider A models for doing this.
Hey, Dylan, there's
another question.
Yeah, it's asking, so which is more difficult for simple settings, such as multi-arm bandits or tabular MDPs, calculating the DEC or calculating the lower bound and the upper bound of regret? So if we can calculate DEC easier, then this is very interesting because we can get the statistical complexity for a new setting easier.
I would say that calculating the DEC is like definitely easier than designing a new algorithm from scratch. Yeah. Hopefully that answers the question. Okay. Yeah, so okay. Let me wrap this slide up. Yeah, so these two properties, like I said, these guarantee that the algorithm will have regret that roughly scales as like DEC M bar. To finish this, you're going to take the max over M bar. Now for this sketch, I assumed that M bar was in the class, but to handle the general case where it can be outside the class, there's kind of another level of this proof based on an algorithmic reduction. And you can look at the paper for more details. Let's see. I will just briefly sketch the upper bound here. So for upper bounds, as I said before, the constrained DEC is smaller than the offset DEC. This means it's harder to prove upper bounds based on it. And I'll just sketch this by focusing on the PAC setting because this is a little simpler than regret. So the way you prove this upper bound is you adapt the algorithm from the original DEC paper, which we call estimation to decisions. And the way this works is it's kind of like a reduction from the decision-making problem to estimation. So for each step, little t, you kind of compute an estimator based on the data you've collected so far. Usually you're going to do this with like exponential weights. So this is kind of like online maximum likelihood estimation. And then once you have this estimator, you just plug it into the constrained DEC and compute the pair of distributions PT and QT that minimize this thing with MHAT plugged in. Okay, and once you have these, the way you explore for the PAC setting is just by sampling the decision to play from QT. Okay, so to prove that this strategy works, the first thing you kind of see is from the definition of the constrained DEC, whenever the true model M star is like inside this Hellinger ball around around M hat T, the risk of the corresponding exploitation distribution PT is going to be small, just like by definition. So it's never larger than the PAC DEC. That's what we want. The only challenge with this strategy is like, in general, M star will not be inside the Hellinger ball for every round. It only will be inside it for certain rounds if the M hat, if the estimator, kind of gets lucky and is actually close to it. And because like the exploration distributions are changing over time, you don't have any guarantee that says like M hat T is like uniformly converging towards M star. But what it turns out is if we're using like a consistent online estimator like exponential weights, M hat will be close to M star on average across all the rounds. And in particular, with this choice of epsilon at the top of this slide, you can show that just by Markov's inequality, M star is going to be in this Hellinger ball for around like half the rounds. And so what this means is that to find a round where PT has good risk, all you really need to do is just repeatedly guess an index T uniformly at random and like check if the corresponding PT has low risk. And this will converge in like a logarithmic number of rounds. Okay, that's the idea for PAC. I'll just very briefly say for regret, things are a little more complicated for regret because like you need almost all the rounds to have low risk. Like just saying that half of them are good is not sufficient. What it turns out you can do here is you can run a scheme similar to what I described for PAC, but you do it repeatedly on kind of like a schedule of like doubling epochs. And at each epoch, you use the results of the previous epoch to kind of like bootstrap the algorithm so that it has low risk at every step, regardless of what happens. Okay, that is going to be concluding the main content of the talk. I'm just about done. I just want to give one quick teaser for a piece of related work, and then I'll conclude. So, okay, we've kind of shown that this constrained DEC, it gives guarantees that are kind of the best we can hope for based on the DEC. And this is cool, but this does still fall short of giving like the tightest possible results for every single model class. So I just want to sketch one kind of approach for going beyond this gap and getting better upper bounds, specifically in the context of RL. So, okay, to motivate this, this is very closely related to the discussion we had with Nan about, like, you know, does the algorithm needs to change for the upper bound, right? So the reason we have upper bounds that scale with this estimation complexity, like this log m, this is because we're doing estimation with respect to Hellinger distance, and this is far too stringent as a notion of estimation performance in general. So if you want to get guarantees that are tight for, say, like model-free RL settings, or like RL settings where we're interested in working with value functions, you know, these should reflect the fact that we only care about estimating the value function well, not the true model. And a natural way of doing this is like just change the divergence with respect to which we perform estimation. So like on this slide, all I'm doing here is, like, instead of using Hellinger, I'm just using like a user specified divergence, right? So this could be, you know, like squared error between the means if I'm working with bandit problems. Or for RL, you could imagine using something like squared Bellman error, or like average Bellman error for the models. And these are both natural divergences to work with if you want tighter guarantees, because they only depend on, you know, the model you're looking at through some sufficient statistic, like the mean reward or like the value.
I'm a little lost here because this is something I wanted to ask, but I thought it's for a different question. Because like, you know, what's the situation in the model-free case? But
yeah,
but previously you were talking about the model-based case, right? So it's
yeah,
like there's this model class MCal.
Yeah.
Not only the analysis knows, but also the learner knows. So the learner has the right to take out a model-based approach.
Right.
In that case, if you like, I could make a choice between do something like MLE versus doing something model-free. Like that's my choice as a learner.
Yeah.
But you would think that if I'm doing MLE, I'm making a better utilization of the amount of information that is there in the data.
Right. So if you have a model class, so let me explain. So for this, even though I've written this slide in the language of models, what actually will happen here, right, is like, so you only care about the first argument to this divergence, which is your estimator. And, you know, this is only going to depend on like the value function or like the average reward function. So like, even though I wrote this in the language of models,
no. Yeah, I understand it.
But value function class.
Well, my question is that this definitely seems interesting, but doesn't seem to, at least to me, it doesn't seem to address the question earlier, right? For example, I think we discussed this before, like in some other occasions, like having something like this may allow you to apply to the case where you only have a value function class, right? Yes. Which means that the corresponding model class that could induce this value function class could be infinite with unbounded complexity. But only the value function has bounded complexity. In those cases, maybe you have no choice but to do this. Right? But when you talk about tighter upper bounds, the thing I was interpreting it as, oh, we're still in the same setting as before. So let's say we have a well-defined model class. Learner knows it. It's finite and the log cardinality is small.
So I guess I'm just going to preempt you and say, like, the first thing you described was right. So like really this is just going to be in a value-based setting where like, you know, you can interpret it as there's like an induced model class that's too big, so we're not actually estimating it. But like, like that's the setting you're in. I would say you can still interpret this as like a special case of the model-based setting, but that's a sort of like abstract perspective on this for sure.
No, I mean, like if you have a model class, there's like suppose the setting is model-based, right? So
but I guess the point of this is not to do model-based. The point of this is to do model-free.
It was like you can still do this, but my point is that you can still do this even if you're in a purely model-based setting. No one prevents you from doing this. But I suspect that this wouldn't give you more edge and advantage and improvement.
This is meaningful for model. Like the point of this is to get meaningful guarantees beyond the model-based setting. Like if you truly have a small realizable model class, you should just do MLE. Like that's only going to be more powerful. For sure. But at any rate, I don't want to spend too much time on this because this is just an advertisement for a different paper. So I'll just quickly finish this. So so as the kind of discussion we just had is getting at, right? The hope here is that like by changing the distance with which you perform estimation, and by also changing the DEC to work with this distance instead of Hellinger, you know, you can get guarantees that don't require a realizable model class, right? Like that maybe only require realizing like the value functions. This actually is not enough on its own, but this does work if you combine it with this technique developed by Tong Zhang called, we call this optimistic estimation. So this is like a technique from this Feelgood-Thompson sampling paper. And the idea here is you still do online estimation with respect to whatever divergence, but you kind of add an extra like optimistic term or like feel good term to your estimator that like biases it towards models that overestimate the optimal value. Okay, so if you do this, then yeah, for value-based RL settings, you can get guarantees based on the DEC that replace like the log cardinality of the model class with something like a log cardinality of your value function class. And in general, what you get is upper bounds that are based on kind of like an optimistic variant of the DEC. And this is something that can be tighter than either the original DEC itself or tighter than like what this Feelgood-Thompson sampling can achieve individually. Okay, so you can check out this paper for more details, but I just wanted to shout this out as like, what is an example of how you can go beyond this gap between the upper and lower bounds? Okay, we're about at the end of the talk. Let me summarize because I think we're definitely at time here. So yeah, we saw that this DEC, this gives a complexity measure for interactive decision-making that leads to upper and lower bounds on the optimal sample complexity. The point of this talk was just to close these upper and lower bounds from the original DEC paper and get kind of the best that we can hope for with this type of complexity measure. There's a lot of future directions I'm interested in here. I'll just mention a few. On the technical side, right, the obvious question is, can we get a complexity measure that's even better? This is pretty interesting, but I think it definitely requires some pretty substantial new ideas. On the algorithmic side, okay, I won't spend time on this right now, but I think like actually deriving like practical algorithms from this framework is a pretty interesting question. I guess for the contextual bandits, which is like Horizon 1, we have practical algorithms from this framework. That's great, but I think like the longer Horizon settings definitely require more development. And beyond that, I think it's also just very interesting to go well beyond the basic online RL model. And this is something we've been thinking about a lot in the last year. So you can kind of view all the results I presented today. These kind of fit into a broader landscape of work that just tries to kind of like strengthen the original guarantees based on the DEC and generalize these to like increasingly rich settings. I'll just briefly give an overview of the landscape here. So on the top row, we have these results for just kind of like the standard framework I gave in this talk. You have a fixed underlying model that you're interacting with. The second row is going from like the basic online RL, online decision-making framework to more rich settings, right? Things like equilibrium computation when you have multiple agents, or settings where the underlying model is changing from round to round, or even things like reward-free RL. And then this last row, we kind of have guarantees that are not changing the setting, but are just trying to be like tighter or more refined. So things like instance optimality. So there's been a lot of development here. But yeah, hopefully this is just the beginning. I think I'm like optimistic that these techniques will continue to find use. And I think there's a lot of interesting questions when we go beyond the basic online RL setup, especially to these more refined settings, like things like instance optimality. Like I didn't really discuss this in the talk, but like, yeah, if you go to things like multi-agent setting, or if you go for like instance optimal guarantees, then just even getting bounds that are like even as tight as like the ones we have in this talk is like very difficult. Okay, I think that's about everything I wanted to say. So I can stop there and like take questions now.
I have a question. If you go back to the last slide,
yes.
I noticed you put this paper under this partial monitoring heading.
Oh yeah.
And I had a question like, so here, if I recall, we assumed that the reward was observed, right?
Yeah.
And like, how does, like, just in general about this partial, like, how does this relate to the partial monitoring stuff? It looks very like similar, right? Except with this extra assumption.
So when I say partial monitoring here, I'm just talking about so it's literally just the same setting as this one, except that you don't see the RT. It's just
right.
you see the OT.
Yeah, I was gonna say when you mentioned that, it seems to me that just let OT to be observable seems the more general setup, because
Yeah,
you
totally.
can always let RT to be part of OT if you want to.
Totally.
Like, yeah.
Yeah.
Right. So how does the story look there? Like, have you looked, like, is there things that you've tried with this DEC stuff without the R being observed?
Yeah, so that's like in this paper that I was that I had on the let me see. Yeah, so that's like in this paper if you want to like look at the references. So yeah, so like the general idea of the techniques here extends, but we do actually use that the rewards are observed in a non-trivial way for like the lower bounds in the work I presented today. And if you don't have that, the lower bounds get weaker. Now, they don't get weaker like qualitatively, in the sense that like the gap between like the sort of best upper bound, like lower bounds you can get in the fully observed setting versus the partially observed setting, you know, is never worse than like root t versus t to the 2/3 factor. But there is a gap between the upper and lower bounds we get that's not there in the fully observed case. But the interesting thing that we proved in this paper on this slide is like, that's actually like fundamental in a certain sense. Like we actually showed that like somehow no complexity measure that only looks at the model class through like the average reward functions and through like pairwise divergences can close this gap. So somehow to close that gap, you need to go even further beyond like what I was presenting in the talk today. So
what specifically about the gap that this particular reasoning is referring to, the log m gap, or
no. So that's what I'm saying is like this is a different one that's only there for partially observed.
Oh, the partial model.
Yeah.
So there's something I also wanted to ask about the tightness claim, right? So this, you claim that it's tight in certain place in certain scenarios, and for upper bound, and in other scenarios for lower bound. Therefore, you can improve it. So, you know, I think these statements are often like extremely subtle, and
it's a subtle like qualitative statement, right?
Yeah. One thing I was thinking is, for example, like okay, so this is actually only two different questions, but let me ask them together. So one thing I notice is that, you know, like this either the epsilon parameter or the lambda or something, like the Lagrangian parameter in the offset version. They essentially do this exploitation trade-off, right? It's how much you want to do information gain versus caring about exploitation. Minimizing instantaneous regret. And in the actual algorithm, that's usually said to be a particular decaying schedule. Right, like a 1/root t or whatever. But in the upper bound, in the lower bound, it's okay. But also in the upper bound reduction, it's minimizing over a fixed schedule. Right. I don't even know it's called a schedule because there's no t in that amount. So is that possibly a source of looseness, or?
I would be okay. So I guess I can have a couple comments on this. So like, it could potentially be a small source of looseness, but like I would be quite shocked if that's a source of looseness in a way that's like conceptually interesting. Okay.
That's my guess, but I guess my real question is like, it's not really specific to this, but when you describe that situation where upper bounds are tight in certain cases and lower bounds are tight and so on, is it still possible that it's just because of analysis looseness like this or something else, such that the analysis actually produce a loose analysis happens to produce tight bounds in certain areas, which means that you still can't rule out that this is the gap is fundamental to the DEC definition. That maybe with a better analysis, for example, the upper bound would be improved in those cases that is currently loose.
Right. So like,
that's where I said like all kinds of loopholes.
I understand. I guess it's so when we talk about like possible looseness here, I would say we're really focusing on like the upper bound rather than the lower bound.
Sure.
I mean, for the lower bound, well, you could imagine trying to strengthen the lower bound, but like this, I would say would involve introducing like at least some kind of new complexity parameters of interest if you're trying to just like make the epsilon bigger. For the upper bound, like I have trouble, like I would be a bit surprised if you could just strictly improve the upper bound as is without replacing like Hellinger with something else. Like I think as soon as you put like an information theoretic divergence in there, it's yeah, it seems it seems difficult to avoid paying for the complexity of estimating with respect to that divergence, unless you could like both show that like, yeah, unless you could show that, you know, for example, the DEC, even though it's written in terms of Hellinger, actually only depends on some sufficient statistic of the models, and that somehow you're able to like even though you're doing like an MLE like algorithm, that is somehow like estimating whatever sufficient statistic you care about at a faster rate than it's estimating like the full distribution. Like, I guess technically that's conceivable, but I would find that surprising. I would like if you asked me to try to prove that in the next 24 hours, I would probably try to find a counterexample. Does that make sense? Is that like a satisfying answer at all?
Yeah, well, I guess I'm just saying that, like, I'm definitely willing to take your, like, take what you said as a strong, like, indication or a strong belief, but
yeah,
it feels to me that this chain is, like, you know, because the upper bounds are tied and lower bounds are tied in different places, and so on. Therefore, you can't get something that is better as long as you stick to the DEC definition. I feel like that's more of a strong belief than a rigorous.
That's fine. I'm willing to say that that's a strong belief. Yeah. But I'm just saying, like, yeah, that's fine.
Yeah.
I mean, it's like, I mean, that's like being negative about like my own thing. So it's not like,
it's just like working along, or like having seen many cases and before, I've learned to just really like make a really clear cut between interpretation, soft interpretation, and strong beliefs with something that is 100% rigorously proved. Because I mean, there are many cases where our strong beliefs just turn out to be wrong.
No, I mean, like, there's a very rigorous statement here, which is just you cannot uniformly improve the choice of epsilon in like the upper bound or the lower bound.
So that I get,
without having to depend on like
specific
problem-dependent quantities of interest. So, like, if you want a rigorous statement, like that's the rigorous statement. You can spend, you know, however much time you want, like interpreting that further.
Yeah,
like,
I'm just saying, like what you said is a very more seems to me a more attractive, more appealing statement that says if you stick to this DEC definition, you can't ever improve significantly over that. But I think that's a little extra leap of faith.
Yeah, for sure. Right. Like, so, like, again, like, and I would say I'm like optimistic you can do better using like DEC like things, but I'm just saying I don't think you can do it without at least changing it a bit in problem dependent ways, right? Like, but time will tell.
Any other question from the audience?
I can ask one more about the computation thing.
Oh,
so,
yeah.
like, I just thought, like, just remembering and looking at like this. So in E2D, like, is the computation part? Is there a computation issue with estimating the like m hat thing as well as solving like the minimizer, like DC as well?
There definitely can be, depending on what the model class is. Like,
right.
If you're just going to use like the most generic estimator, right? Like, this is going to, it's like online learning, right? So like the most generic estimator out there is just like exponential weights. So like this has a weight in memory for every model in the class. Like that's a lot of memory. That's not really like an implementable thing, right? Now, obviously, you can go beyond that for like various classes of interest, but there's not like, I don't think we like have a unified understanding of like what is the most efficiently that you can perform online estimation as a function of the model class of interest.
Oh, and actually-
Thinking about it, like
But
look
yeah.
at the DEC algorithm, it requires outputting a distribution of our policies, right? So like,
yeah, that's
most
the other
practical
one, right?
cases-
It's just, like even if that part's not an issue, like just naively, like as stated for this thing, like you have you are maintaining a distribution over the entire policy space, like if you're doing RL. So again, it's like I have one weight in memory for every single policy. Again, that's
right.
not a good memory requirement. Now, like
unless you can sparsify it or something.
yeah. So like if you look at like the original DEC paper, right? Like for basically all of the examples we have in there, you can, just stare at this thing and like think about it a bit and come up with a distribution that solves this that has low memory, that is sparse. Like for tabular RL, I only need it to be supported on like SAH policies. But like this is another thing where like we don't have like a unified understanding of like when can you do that? Like when can you sparsify this thing? That's a very interesting question also.
Mhm.
Yeah.
And I just remembered on the last slide, or the one like before the references, you had something about running experiments.
Oh yeah. That's
Is
just for contextual bandits.
Oh, I see.
Yeah. I just like Square CV. If you know Square CV for contextual bandits, like that's just a special case of this. So it works great. You can do experiments. Yeah.
Is there any other questions from the audience? If not, I'll probably stop recording now.